What do we do when we fall, Bruce? When that day comes, even I won't want to say it. How are you guys doing today? You want to know where I got these scars? Wow, it's been a while since I saw those. Alright, ladies and gentlemen. It's time to take off the mask. It's kind of heavy. Like there's a weight on the bridge of my nose. You guys ready to start the day? We have a job to do. Gotham needs us. All right, welcome everybody. It's Wednesday. It's a new day. It's a new day. In this new life of quarantine, are we doing a Batman-based problem? I have a couple of those locked away. I should get those rolling. It's a new day, everybody. We're putting one foot in front of the other, taking one day at a time, learning new things. We're having a good time, though. All right, everybody, we're going to recap where we are and where we're going. Excuse me. So, we've been talking about state feedback control, which is another really great way to design controllers. It's probably the most popular way. In industry, academia, whatever, it's more popular than root locus, I think. And so we've been working on an example problem where we're trying to balance this pendulum. And the way we're doing it is it's mounted to this cart that can translate back and forth. And we're controlling the horizontal acceleration of that thing. All right. And then what we're measuring, and this is important because this is going to come back later, we're measuring this angle here. And we're not measuring anything else. So let's follow this flow chart. The first link is we applied Newton's laws to this. And we came up with this second order continuous linear differential equation. And, we have the numbers here. This is if L is 1 meter and if G is 9.81 meters per second squared. And because we're using digital controls techniques, we want to control this with a computer. We're converting this into a discrete time model. But I told you the easiest way to go to a discrete time model is first to put your continuous time model into state space form. So here we're just we're going to define our states as well as define our input and output. So the output is what you measure. So that's the angle of the pendulum. The input is your control signal, U, which is the acceleration of the base. And there's an infinite number of ways to define your states, but the easiest way is to just define the states as your dependent variable and take the derivatives of that. So we define state 1 to be the angle and state 2 to be the angular velocity. And then we put this in matrix form. So we put the equations of motion in matrix form. And so there's 4 matrices that come out of this. There's A continuous, B continuous, C, and D. And I don't put a continuous subscript for C and D because it's going to turn out to be the same matrix for discrete time. So we don't have to make that distinction between continuous and discrete for C and D. All right, so we have a linear continuous time state space model here, and we're going to convert this into a discrete time model. Now, when you convert to a discrete time model, you always have to know what your sampling frequency is first, because a discrete time model is tailored exactly to the sampling frequency that you're working with. So we said for this, let's say we're doing 20 hertz, 20 times a second. So, like I just said, getting the C and D matrices, that's easy because it's the same thing that you have for your continuous time model. A and B, you have to use these formulas. And this is what we get. So we did this last time. So we have our discrete time A matrix, and we just call it A without any subscript. You get a discrete time B matrix, and you get C, and you get D. And that's the easiest way to get a discrete time model. All right, but let's say you want to use the root locus method, which we've been using transfer functions for that. Here's how you get a transfer function from your discrete time model. So this thing is g of z, your transfer function. And last time we did those matrix calculations, and it comes out to be this transfer function right here. 0.0019z plus 0.0019 divided by z squared minus 2.0 blah 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 blah. It's a pain to calculate the transfer function by hand. So I showed you a command in MATLAB, state space to transfer function. And I would suggest you use that instead of doing it by hand. No. And this is the chain of events that has led us to where we are today for this pendulum problem. So what I said at the end of last time, we're we're at the point where we're going to, actually do some control. Because this is just our plant, which we know is unstable. This thing just wants to tip over. That's easy to imagine. So we're going to implement control to make it balance. When you're doing state feedback control, it's easiest to show how it works if you put your model in controllable canonical form, which is a state space form. So that's the first thing we're going to do today. Converting the system to controllable canonical form. What is the ZL in the transfer function? I don't know what you're talking about, my friend. There's some Z's in there. I don't know what ZL is. Okay. Oh, Z times identity matrix? Oh, yeah. This right here is the identity matrix. And it's the same size as your A matrix. So in our case, our A matrix is 2 by 2, so we need a 2 by 2 identity, which is just 1, 0, 0, 1. Okay. You are welcome, Jean, and thank you, Danny, for clearing that up. All right, so we're going to use this template over here to say if you have a transfer function that looks like this, then for controllable canonical form, it should give you A, B, C, D that looks like this. So the first task is to write out like what these B naught, B1, blah, blah, blah terms are. The first thing I want you to recognize, the denominator of the transfer function has z to the n. So n is the highest power of z in the denominator. So if you look over here, the highest power is 2. So n is 2 in this case. So like writing it in the language of this table, I'm going to have zn plus a1, well actually let's do z squared, plus a1z plus a2. So that's the denominator. So like a1 is going to be minus 2.037. A2 is going to be 1.001. And then looking at this table on the right, B naught is multiplied by z to the n, which is z squared. But I don't have anything in the numerator multiplying with z squared. So I know that like this B naught term is it's 0. And then I'm having plus B1 times z plus B2. So B1 is this guy. B2 is this guy. So B1 is equal to B2, and they're both 0.0019. So once you have that mapping between the coefficients, we're just going to build our state space matrices. So we're going to have A is going to be 0, 1. And then I'm looking at this over here. The last row is minus an minus an minus 1. So an is a2. So this has to be minus a2, which is basically just minus 1 because it's like 1.0001. And then this one next to it is minus A1. A1 is minus 2.037. So this is going to be positive 2.037. The B matrix is always the easiest part for controllable canonical form. It's just going to be a bunch of zeros and then a 1 at the bottom. Just looking like this. C is going to be Bn. Well, first I want to look over here. Like all this stuff is subtracting like something times B0. We know B0 is 0, so like all of this stuff that gets subtracted in the C matrix, we don't even have to worry about it. So I just know that my C matrix is going to be Bn, Bn minus 1, blah, blah, blah. So Bn, which is B2, is 0.0019. And then the next one is B1, and that's just 0.0019. And then our last matrix is D. D is equal to B0, but that's 0. So D is just a scalar, 0. So easy as that. We converted our transfer function into a controllable canonical form state space model. Now, one way to check to see if you did this right, this is what I like to do. Check the eigenvalues of this A matrix, because these eigenvalues should be the same as any other A matrix in state space form. So like we have an A matrix from before, which was this one, 1.0185. So I'm going to put this one into MATLAB. I'm going to calculate the eigenvalues, and I just want to verify that the other A matrix we calculated has the same eigenvalues. Let's clear this. So I'm going to say A, let's put our old one in here, 1.0185, 0.0503. Then we go into the next row, 0.7403, 1.0185. So that's the old A matrix we have. To get the eigenvalues, you use the eig command. So the eigenvalues are 1.2 and 0.82. And notice that eigenvalue, which is the same as like a root or a pole of your system, it has magnitude greater than 1. So this system is unstable, which physically makes sense. If you try to balance something in your hand, it's going to topple over unless you correct it. What's the difference between the discrete time model ABCD matrices and the controllable canonical form of them? The only difference is that they're, like in terms of linear algebra speak, they're expressed with respect to a different basis. But the eigenvalues are going to be the same. So so this is our controllable canonical A matrix that we just came up with. 0, 1, minus 1, 2.037. And let's call this A2 so I don't like overwrite my other one. And if we get the eigenvalues of this, they're the same, 1.21 and 0.82. So, in a second, we'll see that if you're calculating your gain matrix by hand, it's much easier if the equations are in this controllable canonical form. So we won't always be going to this form in the future, but this is going to make this next step a little bit easier. Yeah. There's an infinite number of state space forms that will return you back the same transfer function, which is kind of cool, but it can also be a little daunting. Okay, so we have this. Now we're just going to store that away. We'll pull that out, use it later. But let's talk about our state feedback approach again. So this is what we call our state equation. These are where our control signals come in. And remember, this can be extended to multiple input, multiple outputs. Right now we just have one output, one input, but we're going to define the control input to be minus k times your state vector. So this is k is the feedback gain matrix. And if you substitute in that expression for u into our state equation, you get this. Xk is a minus bk times xk minus 1, and I like to call this a minus bk your closed loop A matrix. So that's what the sub CL is for. Now here below, this is the whole goal of state feedback control. You want to make the eigenvalues of your closed loop A matrix equal to some target closed loop poles that you're going to pick. Remember, the eigenvalues of the closed loop A matrix, this is the same as your closed loop poles. So if you're thinking about root locus design like you're doing in project 1, you're picking some target poles, and your closed loop poles should be equal to those target poles. That's where the magnitude and angle criterion come in. So for state feedback control though, we want these target poles to be equal to the eigenvalues of this closed loop A matrix, A minus BK. So let's talk about how that works. So we have to bring up what an eigenvalue problem is. So let's write out an eigenvalue problem. So our closed loop A matrix, which remember it's A minus BK, if this is operating on an eigenvector, which I'll call P, and I'm going to give it a subscript I because there's more than one of these. If your A is a 2 by 2 matrix, there should be 2 eigenvectors. If it's a 4 by 4 matrix, there should be 4 eigenvectors. So I just indicates it could be 1, 2, 3, 4. So this is the ith eigenvector. Now here's the special thing about eigenvectors. If you have a matrix operating on one of its eigenvectors, that would be the same as an eigenvalue, or the ith eigenvalue operating on that same eigenvector. So it's saying a matrix multiplication, when it's operating on an eigenvector of that matrix, it's the same as just multiplying that eigenvector by a scalar, which is just functions to scale the vector. So it's a special case. So this is what we call the eigenvalue problem. If you find an eigenvector and an eigenvalue that satisfy this relationship, well, that means they're eigenvalues and eigenvectors. So this is the ith eigenvalue. Now here's the special thing for controls. We're trying to design this closed loop matrix so that we place the eigenvalues where we want. So like, I want the eigenvalue to be z star. Well, that also implies like there's, like these starred eigenvectors that go with it. Okay, so let's keep running with this. If we bring this left-hand side over to the right-hand side, we're going to have our desired eigenvalue times an identity matrix, which just returns the eigenvalue itself, minus our closed loop A matrix, which instead of writing out I'm going to write out all the terms in the closed loop A matrix. So that's A minus BK, right? So this, operating on my ith eigenvector, should evaluate to 0. And I put a little line under this because it's a 0 vector. It's a vector full of zeros. So all I did was move our closed loop A matrix times the eigenvector over to the right-hand side. And so z minus that. Okay. Now here's the thing. This eigenvector, it's not 0. Like all of this stuff, the product of these two is equal to 0, but I know the eigenvector is not 0. I also know that this matrix is not 0. So you have the product of two non-zero things evaluating to be 0. So the only way that this can be true, that both of these are non-zero and yet the product evaluates to 0, that's only possible if the determinant of this matrix equals 0. Well, and this just means that this matrix is non-invertible. Because if it was invertible, then I could just multiply the left and right hand sides by the inverse of this matrix. And the result of that would be that the eigenvector is 0, which we don't want. All right, so we have this eigenvalue problem. And the reason we're setting it up is because we want the eigenvalues of the closed loop A matrix to be what we decide as the control engineers. The result of this eigenvalue problem is that this equation has to be satisfied. And this is the characteristic equation of the closed loop system. If you look at this, like assuming that we define our target poles, then this term is known, the identity matrix that's known, A is known, B is known. So we have to solve for our feedback gain matrix from this. So we're solving for K from this characteristic equation. And it may not make sense to you yet, and that's why we're going to do an example. Okay. So the first thing we're going to do is we're going to pick some target closed loop poles for our inverted pendulum system. Actually, I'm going to pick them. You have no say in the matter whatsoever. It's done. So if you choose a settling time of 1 second, and if you choose an overshoot of 20%, and if we choose a sampling frequency to be consistent with what we've set up our model to be, 20 hertz, we get these target poles. So we want these to be the eigenvalues of our closed loop A matrix. Okay. So let's set up what we need our characteristic equation to be if we want these target roots. Okay. And let's simplify these a little bit because I don't want to write 4 decimal points. Let's say these are 0.76 plus or minus 0.31 I. So just from these two roots, we know what the characteristic equation should be. So like it would be z minus 0.76 minus 0.31 I plus 0.31 I equals 0. I'm going to move this down a little bit. So if you look at this, the roots of this equation, so when it equals 0, is if you plug in these values, right? It'll make the equation go to 0. So if you multiply this out, I'm going to skip these steps for you. You get a characteristic equation of z squared minus 1.52z plus 0.6737 equals 0. So if our closed loop A matrix turns out to have this characteristic equation, and we know the roots of this characteristic equation are those target closed loop poles. So if we can get this to work out, then we will have achieved our goal. So here's the way you do that. We know that from up above, the characteristic equation of our closed loop A matrix is equal to the determinant of z star I, minus A minus B. So I'm going to do minus A plus BK. And this should be equal to z squared minus 1.52z plus 0.6737. And let's just get rid of the star for now, whatever. So you see what I did here? I know that this is what I want my characteristic equation to be. And I'm going to solve for k so that this determinant is equal to that stuff. So let me show you how it works. So first we're going to expand out this expression in here. So the determinant of z times I, that'll just be z0, right? That's z times a 2 by 2 identity matrix. And then I'm going to subtract a, which was 0, 1, minus 1, and 2.037. And then I'm going to do plus my B matrix, which was just 0, 1, times my K matrix. The K matrix, it ends up in this case having to be a 1 by 2 matrix. Jonathan says minus B matrix, A minus BK. You're exactly right, but because it's minus and then the whole quantity is A minus BK. So that ends up being like minus A plus BK. So I just got rid of the outside parentheses there. Yep. Okay, so I'm going to multiply, well, I'm going to add these two. I'm going to multiply this one out. And so let's just go to the next line. So this is equal to the determinant of, so this is, I'm going to combine these two, z minus 0, minus 1, 0 minus minus 1, so that's plus 1, and then z minus 2.037, and then to multiply these two matrices together, it's going to be 0 times k1, 0 times k2, which is just, 0, 0, and then 1 times k1, 1 times k2. And then we're just going to keep rolling with this. So now I'm going to combine these two matrices. It's going to be the determinant, okay, of z plus 0, so that's z, minus 1 plus 0, so minus 1, 1 plus k1, and then z minus 2.037 plus k2. So at this point, we broke it all down into a 2 by 2 matrix that we have to take the determinant of. And it might have been a while since you've done the determinant of a matrix. But what you do is you take these diagonal terms, you multiply them together, and then you subtract from that this. Abhijit says, how do we know the order of the K matrix? It has to be of a size that makes the linear algebra work out. So like, I know that this is the B matrix times the K matrix up here. And let's forget, that I've written out the K matrix already. But I know that B is a 2 by 1. And the product of B and K, I'm going to be adding it to these 2 by 2 matrices later on. So that means the product of B and K has to end up as a 2 by 2. So the only way that can happen is if I multiply a 2 by 1 with a 1 by 2. Okay. So if I take the determinant, I'm going to have z minus times z minus 2.037 plus k2. And then I'm going to have minus negative 1 times 1 plus k1. All right. So this is, so I'm just going to multiply this out. Z squared plus K2, looks like my pen is, it's not wanting to do its job. Come on, buddy, you can do it. K2 minus 2.037 times Z plus K1 plus 1. And then remember, we already know what we want this characteristic equation to be equal to. If it's going to have the roots that I specified, it's got to be equal to this. So I know this has to be equal to z squared minus 1.52z plus 0.6737. So solving for these k parameters is just as easy as matching this up. So minus 1.52 has to be equal to this term in front of z. And k1 plus 1 has to be equal to positive 0.6737. And it only turns out to be this easy because we put it in controllable canonical form. So K2 minus 2.037 equals minus 1.52. So K2 is, whoa, 0.517. And K1 plus 1 equals 0.6737. So K1 is minus 0.3263. All right. Okay, this we need to check though if this worked in giving us the right eigenvalues. So I'm going to go to MATLAB real quick. So we defined our A matrix A2 to be this. So that's A in controllable canonical form. Did we define our B matrix? Okay, let's just call it B2. So that's controllable canonical B. And this is the K matrix we just came up with. So K1 was minus 0.3263. And then the second element, the second element is 0.517. So that means the closed loop A matrix is A2 minus B2 times K. Let's take the eigenvalues. wait, first we should put Z star was 0.76 plus 0.31. Bless me. Oh wait, plus 31i. Okay, so let's take the eigenvalues of our closed loop A matrix, and voila! They are equal to Z star and, you know, the conjugate pair that we wanted. So this means our closed loop poles are equal to what we wanted them to be. So that's the first test you should always do after you calculate your K matrix. Build your closed loop A matrix and then see if the eigenvalues are indeed what you want them to be, and they are. Then the next step is you should run a simulation. And so I show you some code right here, and I know we're running out of time. So I'll let me just run through this real quick. You know, standard stuff here. I define like a time vector. I initialize my states, outputs, input. And then I define some initial conditions. So I have to go back. This simulation I didn't do in controllable canonical form, but the end result is the same. So this first state is the angle of the pendulum. So I started at 45 degrees. And then I let this controller try to straighten it back out. So the reason I mentioned controllable canonical form, when you go into controllable canonical form, your states, x1 and x2, are usually not physical states. So it's not defined as like, oh, the angular position and the angular velocity. So I made this controller not in controllable canonical form, just so I could define this. Okay. There's other ways to do it too. We'll show that as well. So here I'm just simulating the response in a for loop. I have my state equation, my output equation. This is defining my control input. It's just minus k times your states. And so this is what the response looks like. Like I started at 45 degrees, and then instead of falling over, the control signal, which is the acceleration of my base, it accelerates to the left really hard. If you think about it, like this is tipped over, and then to correct this again, this base shoots over to the left to get under it. So like this makes sense to me what I'm seeing. And then the control input actually accelerates back to the right, and we can see that this stabilizes back to 0 degrees eventually. Now you should also check if this meets the performance criterion that you specified. Like the way I chose my poles is I wanted 20% overshoot. Let's check that. Oops. If you look like right here, that's about 20% from like where it started. Like it started at 45 degrees, and then it looks like it went to about like minus 10. And if you calculate this difference here, that's pretty close to 20. And then it definitely settles in a time period of 1 second. So it looks like it's doing what I wanted to do. And then I made an animation in MATLAB because that's way more fun to look at. Let's see if I can do this. Let's run it. Continue this. Ooh. Let's do that again. So it accelerates hard to the left. Run it again. Boom. And then it kind of just skates over to the left. Because remember, we were just stabilizing it vertically. We didn't make a control condition that the whole apparatus needs to stop. So you'd have to specify that. So this is what it would look like in real life. I also made one simulation where I made a disturbance input. Let's see. Wait, I want to try this. So I start it just vertically, but then I add this disturbance, which is kind of this pulse thing. And I'll show you what it looks like. Let's see if this works. So what I did is I just had the pendulum start straight up, and then I hit it with this red disturbance. So this is an acceleration disturbance to the right. So this is like simulating me tapping the pendulum to the right, and then the control reacts by accelerating to the left. And then I did a tap to the left, and and the control responds to the right. And this top graph is just showing the angle of the pendulum. So I'll run the animation again. I don't know, I think controls is really beautiful because all of these control decisions are decided automatically by your K matrix, essentially, right? Like two numbers. Those two numbers are always deciding like what my control input's doing. But if you analyze it after the fact, you're like, oh, like that makes sense. Like I would have to move this to the left or the right depending on the disturbance. So I'll show this animation one more time. And then for the sake of time, I know we're running a little bit over today. There's a problem here that I haven't mentioned. And this will lead us into like what we're going to have to do in the next couple classes. Okay, here's a problem with state feedback. U is equal to minus K1, K2 times, our two states, X1 and X2. Right? So this is how I'm calculating the control input at each step. And if you remember, well, this is not in controllable canonical form, but this will get my point across. Like let's say your states, these were two states, theta and theta dot. And so I need both of these in order to figure out what my control input should be. It's K1 times theta plus K2 times theta dot. But remember, I'm only measuring this, the angle. I'm not measuring this. Because I was saying for this example, we just have a rotary encoder that measures the angle, but it's not measuring the angular velocity like a gyroscope would. But to do state feedback, I need to know this as well. And that's the rub. If you're going to do state feedback, you have to figure out a way to get that. And that's going to lead us into the topic of estimation. Because whenever you do state feedback, you have to be estimating the things that you aren't directly measuring. Because you need all of that state information to figure out what the control input should be. So that gets into a really interesting set of problems. It's really fun. But it's a problem we have to address. And with that, That's the official conclusion of our lecture, but I'll hang out, answer questions that you have. Probably another 5 or 10 minutes or so. I hope you guys are having a good day. It's not fun being cooped up day after day. But we will get through it one day at a time. I did not want to get out of bed this morning, so I ended up forcing myself to take a little jog outside. Lewis says, I still don't get the problem of state feedback. Can you say it again? Sure. Okay, so the problem is, like, look in this for loop, because this kind of represents what would happen in real life. Here, Y is your output, which is what you're measuring coming off the system. So for this problem, I measure the angle theta. All right. And then here's where I calculate what my control input will be for the next step. And it's minus k times my state vector. So this is k times theta of k and theta dot of k. Let's say those are my states. I have this one because I measured it. What do I put in there for theta dot? Ike says, so really what we're doing is just changing the U matrix so that we can directly measure it, right? I'm not totally sure what you mean by that, but we'll never, like for this problem that I've set up, we're never going to directly measure theta dot. So I'm making a hypothetical problem where all that I'm measuring is the angle. I'm not measuring the angular velocity. But the problem is my control input to calculate it, it requires me to know what the angular velocity is. So I have to know something that I'm not directly measuring. You see what I mean? You guys are already probably thinking of solutions to this, right? So it kind of just works around it. Well, okay, so I need to say this. Like, this, so this right here, this is where I'm calculating my states, x. Or, so here I calculate but this here just represents what the system is physically doing, and in real life I don't have access to this. So in real life I don't access this. So I don't know the states. This is supposed to represent just like what the physical system is doing. And you have to imagine that the only information that I'm getting is from my sensor. So the only reason I could do this simulation is because I kind of cheated. I said, yeah, sure. So I need this x vector, so I'll just plug in what I calculated here 2 lines before. But in real life, you don't have that information. All you have is y, what you measure with the sensor. So the only way that it worked here today is because I cheated. I assumed that I know. Oh, why exactly use the canonical? Why exactly we use the canonical state space form? So, kind of working. What we can't measure? No. Canonical state space form is not working around what we can't measure either. So, the only reason I used canonical state space form today is it makes it easier to do this set of math that I did by hand. So like calculating this determinant and solving for K1 and K2. Like if you're in controllable canonical form, it allows you to solve for K1 and K2 independently. So like these equations aren't coupled together. Like the K2 term is the term in front of Z. The K1 term is the one that doesn't have any Z. So boom, boom, it's easy to solve for K1, K2. So either next lecture or the one after that, we're going to learn how to solve for these K parameters regardless of the state space form you choose, because we're not going to be calculating these by hand in general. I think it was I just wanted to show you that today. So no, controllable, there's nothing magic about controllable canonical form that sidesteps this problem of you think you get it more. Yeah, it's a tough concept. We'll keep working on it. Lewis says, will it be part of the lecture to learn how to make that kind of animation like a pendulum? I won't cover it directly in lecture, but I can post this. I don't mind if you want to make your own animations. The key to it, and you can save these to videos as well. I didn't do it as this one, but I just make a loop that plots this pendulum system. Oops. And then it just keeps redrawing it wherever it is at the next. So it's just these lines of code. And it's fun, I put a little pause in here that's equal to our sampling period. So I think this is working at the same speed you'd see in real life. It's pausing for like a 20th of a second. Yeah, animations are really fun, and it's a way to like, it gives you a more intuitive sense. It's like, is this right? Is this doing what I expect it to be doing? Sometimes it's hard to figure that out from a graph, but if you see it in motion, you're like, no, that's doing what I think it should do. Question about the project. When calculating the continuous time roots and natural frequency to get the closed loop poles, I use the highest settling time. This gives me poles with a real value close to 1 and imaginary value over 1, which wouldn't show on the root locus grid. Is this right? I think you're calculating your... I think there's a mistake in your calculation of the poles. Because if you have a real value close to 1 and then an imaginary value over 1, Yeah, it's going to be outside the unit circle, which is unstable. So it would never settle. So I don't think that's correct. Whether you pick the high or the low, that's not the problem here. Don't you solve for the natural frequency and plug that value into the continuous time roots formula? You can. Here, hold on. All right. Because let's say so like our continuous roots if you want to pick like a natural frequency and damping ratio, it's going to be like this. And then, like your discrete time roots, which would be like your Z star. That's the exponential of your continuous roots times your sampling period. If these are stable, which means having a real part less than 1. So that means like oh wait. That's wrong. Stable just means you know what I mean. The real part has to be negative for a continuous root to be stable. So if those are stable, the magnitude of these roots is going to be less than 1. There's no way it'll be outside the unit circle. Ike says if you check the notes from February 17th, it gives a good example of solving it. Thank you, Ike. What other questions do you guys have? I mean, I will be back at 3 p.m. So if you can't think of your questions right now, if you're available between 3 and 5 p.m., those are my daily office hours. We hang out, take questions, listen to music. It's a chill time. All right, everybody. I'm going to get some food, and I will return this afternoon. I hope you will too. Have a great day.